Previously, we went over the integrated rate law for first-order reactions. On a graph, you can identify a first-order reaction because the vertical axis will have natural log of concentration of A or natural log of the pressure of some reactant, and will slope downward, with the slope being equal to negative K. Whenever you have a first-order reaction, if you graph it, it will look like this. The slope will be equal to negative K. It will be a straight line. And whenever you are doing calculations, the two equations you are allowed to use are down here in the lower right. Now let's talk about second-order reactions that are second order in just one reactant. In other words, the rate law for the reactions we're going to talk about looks like this. K times the concentration of some reactant squared. And that's it. Notice that this other rate law that I've written here is also a second order reaction. But it is second order only because it's first order in reactant A and first order in reactant B. What we're going to talk about does not apply for that type of reaction. It only applies for reactions that are second order in a single reactant. The equations that apply for these reactions are shown in the yellow boxes. You can see that they are in some ways similar to the first order rate law equations and other ways not. There are no natural logs that appear in these equations. Instead of natural logs, you see we have 1 over something. The one on the right is the half-life equation. And notice that the half-life, unlike for a first-order reaction, does depend on the initial concentration of reactant A, and the half-life actually changes as time goes on. This is very different from a first-order reaction. If we plot on a graph 1 over the concentration of something at any given time, we will get a straight line, and it will have a particular slope. And what slope would that be? Time will be plotted on the x-axis. 1 over the concentration will be plotted on the y-axis. So if we look at the equation that's in yellow on the left, and we say, well, if x is time and y is the 1 over concentration of A at any given time, we're seeing here that, again, this is basically a y equals mx plus b formulation, which means that your slope of this graph is equal to the rate constant. Let's try an example problem. Data were taken on the decomposition of an initial 2.45 molar solution of reactant X. Several graphs were made. The X concentration versus time graph was curved with a generally negative slope. The natural log of the X concentration versus time graph, too, was curved with a generally negative slope. The 1 over X concentration versus time graph was linear, with a positive slope of 4.33 times 10 to the negative third, molarity to the minus 1, seconds to the minus 1. Determine the reaction's initial half-life and the X concentration at 105 seconds. If we look through all of that information, what jumps out to us is this here. The graph that is linear tells us what we want to know. And that is that this reaction is second order in X, because second order reactions, when you plot 1 over the reactant concentration versus time, you'll get a linear graph with a positive slope. In other words, the rate law for this reaction looks just like I've shown here on the right, and we know the value of the rate constant, 4.33 times 10 to the negative third. Molarity to the minus 1, seconds to the minus 1. Let's find the initial half-life. We're going to use the half-life equation. We've chosen the half-life equation for second-order reactions, not the one for first-order reactions. If we do a little algebraic manipulation and solve that for the half-life, we get that the half-life will be equal to 1 divided by the rate constant and divided by the initial concentration, and so we can calculate the initial half-life to be 94.3 seconds. That half-life will change as time goes on, but that's its initial half-life. The other part of the problem says that we need to find the concentration of reactant X at 105 seconds. Let's use the second order in one reactant rate law, which looks like that. Which variable are we looking for here? And that would be this one. The concentration of X at some time that is not the initial time. Remember, X naught is the concentration at time 0. So we're looking for the concentration of X at time t. If we add 1 over x naught to both sides, I'm going to do a little algebra here and solve that for the variable we're looking for. You write that down and check it and make sure that it looks right to you. We could simplify this right side because your math teacher would wet the bed if he or she saw a fraction in the denominator. But we don't get our panties in a bunch about that in science. As long as we can solve it, we're happy. We've got our rate constant, we've got the time in question, 105 seconds, and you can see there's in the denominator 1 over our initial concentration. Type that bugger into your calculator, boom, 1.16 molar. Not surprisingly, lower than our initial concentration of 2.45, because of course this material is going to be consumed, so its concentration is going to drop over time. If you want to take a picture of this on your phone, this would be a really good idea, because this picture summarizes first order and second order in only one reactant reactions. It gives the equations that apply, it shows a sample graph of what each one should look like, and at the bottom it gives my little mnemonic for helping students remember, wait, should I use the natural log form of the equation on this one, or should I use the 1 over equation? There you go. On the left, it's natural to want to finish first. Natural log, first order. It's natural to want to finish first. In the lower right, to want to finish second, that's upside down thinking. In that mnemonic, you've got your second order reaction and you've got the upside down thing. You see, you got the 1 over. Anytime you have a second order reaction, it's the 1 over relation. To want to finish second, that's upside down thinking. Now, sometimes you finish second, and it's not bad to finish second, but to set the goal of finishing second, that's no good. It's upside down thinking. Let's summarize. Here we have gone over the integrated rate law for reactions that are second order in a single reactant only. Note that the equations do not apply to reactions that are first order in each of 2 reactants. On a graph, second order in only one reactant reactions will have the vertical axis labeled with a 1 over concentration of a reactant or 1 over partial pressure of a reactant. The graph will slope upward with a slope equal to the rate constant, K.